Welcome to the deep dive. We take a whole stack of sources, break them down, and basically give you that essential knowledge shortcut.
And today, we are diving deep into something kind of fascinating, a real tech paradox.
Right. A language that's, well, it's older than the internet itself, 65 years old.
But it's still somehow absolutely central to, like, global commerce. If COBOL gets a cold, the whole world economy feels it.
Exactly. We're talking about COBOL, the common business-oriented language, this unlikely digital workhorse.
Yeah, quietly running trillions of dollars, handling almost every big transaction you probably make daily.
Okay, so our mission today is not just about reminiscing about old code, right? We need to get into why it's still so critical.
Precisely. Especially in finance, government, these huge sectors. And we need to explore the challenges. Modernizing this stuff is, well, it's complex.
And frightening, frankly.
And there are cutting-edge strategies, too, right? Ways people are trying to tackle this.
Oh, yeah. Lots of different approaches. We'll get into those. Okay, so the key takeaway for you, the listener, right up front. This isn't just a tech story.
Not at all. It's about reliability. Insane reliability. And the sheer cost, the implications of trying to rewrite the systems that run the world's finances.
Get this number, 95%. 95% of credit and debit card swipes. They rely on COBOL processes running somewhere in the background.
95%. It's staggering. That's not legacy. That's the beating heart.
It really is the backbone. Okay, let's unpack this. We have to start at the beginning. Segment 1, the origins. How did this beast even come to be?
Right. You got to go back to the late 1950s. And the problem then wasn't speed or features. It was cost. Pure economics.
Programming was just getting wildly expensive.
Wildly. There's a survey from 1959. The average cost just for programming at one site, $800,000.
$800,000 in 1959 money.
Exactly. And then, okay, you buy new hardware, which happened all the time back then.
And you have to move your programs.
Yeah. And that conversion. Another $600,000 on average. It was killing businesses.
Yeah. Okay, so that's unsustainable. You can't keep paying that every few years.
Absolutely not. So the goal became clear. We need one language, a common business-oriented language, something to make conversions, cheaper, faster, decouple the software from the hardware madness.
And the push for this didn't come from, like, some garage startup. It came from the government.
Yep. The U.S. Department of Defense, the DoD. They were the crucial sponsor here.
Why did the military care so much about business software portability? It seems odd.
Because they had the same problem, just bigger. They were massively invested. Think about it. 225 computers running already in 59.
Wow.
Another 175 on order.
Sure.
And they'd already dropped over $200 million just getting programs onto those machines.
Okay, so for them, portable code wasn't some ideal. It was pure cost savings. Stop spending that $200 million over and over.
Exactly. Military efficiency driving business language. Kind of ironic, right?
Totally. So tell us about the first meeting, the big one at the Pentagon.
Okay. May 1959. 41 people show up. It's a mix. Manufacturers, users, government folks. Charles A. Phillips is chairing.
41 people trying to agree on a programming language. Sounds fun.
Ah, yeah, I bet. But they actually agreed pretty quickly on three, core mandates. Non-negotiable things that basically defined COBOL forever.
Okay, what were they?
1, maximal English. Yeah, use English words as much as possible. Make it readable.
Okay, readable. Makes sense for business.
2, machine independent. Absolutely critical. Write once, run anywhere, or at least on different machines without a total rewrite.
The original portability dream.
Yep. And 3, easy to use. This was huge. They prioritized ease of use, even if it meant sacrificing some power or, raw efficiency.
So readability and portability over maybe technical elegance. That's probably why it stuck around.
I think so. That design choice was fundamental. So this group, they call themselves CODIS, Committee on Data Systems Languages.
CODIS, okay.
Yeah.
And they weren't starting from scratch, right? They looked at existing languages.
Right. They mainly pulled from 2 big ones. Flowmatic, which was Grace Hopper's baby, and IBM's own language, Contran.
Flowmatic. That's where the English-like stuff came from.
A lot of it, yeah. English words for commands, those long descriptive variable names, super important for business logic. And crucially, separating the data descriptions from the actual processing steps.
That separation. The data division and the procedure division. We'll dig into that later, but that seems key.
Oh, it's massive. Huge step for modularity, managing business records. That's why it works. Now, about Grace Hopper. She gave technical advice for sure.
But the whole mother of COBOL thing.
Yeah, Gene Samet, who was the lead designer, actually said that's not correct. Hopper's influence was more indirect through her staff on the committee. Important historical detail.
Good to know. And you mentioned IBM's Comtran, but there was pushback against IBM.
Well, yeah. Apparently, there was a strong anti-IBM bias among some committee members. They actively resisted using some Comtran features, even good ones like algebraic expressions, because they didn't want IBM to look like they were dominating the whole process. Politics.
Always politics. So the process wasn't exactly smooth sailing. I heard someone even pulled a prank.
Huh. Yeah, the process was slow. Painfully slow for some. This guy, Howard Bromberg, he got so frustrated with the delays.
What'd he do?
He went out and bought a tombstone, a $15 tombstone, which is like $160 today.
Seriously, a tombstone.
Yep, had COBOL engraved on it, and mailed it to the chairman, Charles Phillips, basically saying, this thing is dead on arrival.
Wow. That's
Yeah.
a commitment to sarcasm, a $160 prank.
Shows the pressure, right? But despite all that, they actually did it. Specs approved January 1960.
So the goals were met. Efficiency, portability, low conversion cost, usable by newbies.
That was the claim. And then boom, August 17th, 1960, just 7 months later, the first COBOL program runs on RCA 501. It worked.
A rapid, tense, slightly dramatic birth for a language that would outlive almost everyone involved. Okay, let's move on. Segment 2. COBOL through the decades. It launched, but not everyone was convinced, right?
Not by a long shot. There were immediate doubters. June 1960, some anonymous source is quoted saying it's rather unlikely that COBOL will be around by the end of the decade.
Famous last words. If only they knew it'd be running global banking 65 years later.
Seriously, aged like milk, that quote. But to be fair, the early days were rough. Compilers were slow, like really slow.
How slow are we talking?
Sources say like 3 to 11 statements per minute in 1962. Painful. Imagine debugging that.
Oof. Yeah, no thanks. But then came the turning point, IBM.
That was the big one. Late 1962. IBM basically throws its weight behind COBOL, makes it their main development language, stops working on their own Comtran.
And when IBM commits...
Yeah, it's pretty much game over for the competition. Suddenly, COBOL adoption just explodes. By 1970, it's the most widely used language, period.
Okay, so dominance achieved. And then comes standardization. ANSI standards.
Right. You get COBOL 61, COBOL 65 adding things like disk storage, tables, then the formal ANSI standards, COBOL 68, COBOL 74. Standardization is good for portability, but...
But it causes problems too. Incompatibility.
Yep. COBOL 74 made like 44 changes that broke older code. Annoying. But the real fireworks, the big drama, came with COBOL 85.
Ah, yes, the COBOL 85 controversy. This is where the users actually fought back, threatened to sue the standards guys.
They did. The big fear was the conversion cost. Imagine you're running a massive company like Travelers Insurance. Their VP, Joseph Brophy, said they had 40 million lines of COBOL.
40 million lines in the mid-'80s.
Yeah, and he saw the proposed changes in COBOL 85, the incompatibilities, and basically said converting would be a complete waste of our programmer resources, threatened a lawsuit.
And he wasn't alone, right? This was widespread pushback.
Oh, totally. The initial review got something like 1,700 negative letters, basically a programmer revolt. They were terrified of the maintenance nightmare.
But it still went through. COBOL 85 happened, and was it actually that bad? Or did it help in the long run?
It was painful, no doubt. But ultimately, yeah, it was crucial. It brought in features that really helped with maintenance and structure.
Like what? What were the key improvements?
Big ones were the explicit scope terminators. Things like end-if, end-perform. Sounds small, but it makes reading the code and debugging so much easier.
Yeah.
Clears up the control flow.
Okay, ending the blocks properly. What else?
The evaluate statement, which
Right.
is basically like a modern switch or case statement, super powerful for handling multiple conditions cleanly, and inline perform loops, so you didn't have to jump to a separate paragraph just for the loop body.
So making it more like, well, structured programming.
Exactly. It was a big step in that direction. Then, moving into the 90s and 2000s, COBOL didn't just sit there. It started absorbing ideas from newer languages.
Like object-oriented programming. From
Yeah.
C++ and Smalltalk.
Yep. Started adding OO features.
Yeah.
But the really big leap was COBOL 2002. That was a major modernization.
What came in with 2002?
A lot. Freeform code finally got rid of those strict column rules. Recursion became possible. User-defined functions. Crucially, support for things like Unicode for international characters, floating point and binary data types, even a screen section for building text-based user interfaces.
So it was really trying to keep up. And it's still being updated. This isn't just a museum piece.
Not at all. It's a living standard. COBOL 2014 added things like method overloading and, really important for finance, portable math using the standard IE7504 format for floating point numbers.
Ensures calculations are consistent across platforms.
Exactly. And the latest one, COBOL 2023, just came out. It's adding stuff clearly aimed at modern systems. Asynchronous messaging with send and receive, transaction controls like commit and rollback, even a simple delete file command.
Wow, so COBOL is actively evolving to talk to the modern world, not just exist in its own bubble?
That's the picture, yeah. It's not just being maintained, it's adapting.
Okay, that resilience is incredible. Which brings us perfectly to segment 3. Where is all this COBOL actually running today? Which industries depend on it?
Honestly, it's almost easier to ask where it isn't. It's global. Retail, travel, healthcare, insurance, logistics, and of course the big ones, finance and government.
The scale is still mind-boggling, right? That Gartner estimate from '97.
Yeah, 80% of the world's business running on COBOL. Over 200 billion lines of code back then. And they estimated 5 billion more lines were being written every year, even in 1997.
Just unbelievable accumulation. And the core reason it persists, especially in finance, seems to be reliability and batch processing.
That's the heart of it, yeah. It's the financial system's backbone. Nearly half of all banking systems worldwide still rely heavily on COBOL.
And those transaction numbers?
95% of ATM transactions.
Sure.
80% of in-post and bank counter transactions. It's just built for that kind of massive overnight batch processing, reconciling millions of accounts, and high-volume transaction processing that needs to be fast and, more importantly, perfectly accurate.
And governments are just as hooked. We saw that during the pandemic.
Oh, definitely. Government systems need that same scale and long-term stability. You look at U.S. federal agencies in 2016, Agriculture, Homeland Security, Justice, Treasury, Veterans Affairs, all reporting critical systems running on COBOL.
And the IRS example during COVID, trying to get stimulus payments out?
Right. They had to scramble to patch their COBOL-based individual master file, a system decades old, suddenly needing to handle an unprecedented flood of payments. It really highlighted that dependency. Worth noting, though, the IRS is now, finally, transitioning that system to Java.
Okay, so they are moving off it eventually. But it begs the question, why? Why are these absolutely critical systems still running on this, ancient tech?
Two main reasons, really. One is just the sheer proven reliability of the platform it usually runs on, the mainframe.
The mainframe itself is the key.
It's a huge part of it. People who work on them describe mainframes as dead-on reliable. They're engineered for uptime, hot swappable parts, redundant power, specialized operating systems like ZOS. They just don't go down the way distributed systems sometimes do.
And the second reason, security.
Yeah, but it's kind of security through obscurity, or maybe security through specialization. It's not that COBOL code itself is magically secure.
It's that hacking a mainframe requires a different skill set.
Exactly. The number of people who deeply understand mainframe architecture and ZOS is way smaller than the number who know Windows or Linux internals. That lack of widespread hacking knowledge makes them a harder target. Combine that bulletproof reliability with a smaller attack surface, and you can see why banks are hesitant to replace something that just works day in, day out for decades.
That makes sense. Risk aversion is huge in finance. It's also worth pointing out COBOL isn't only on mainframes anymore, right?
Vital point. Yeah, while ZOS is its traditional home, modern COBOL compilers let it run pretty much anywhere. Unix, Linux, Windows, OpenVMS, you name it. It can integrate with more modern systems.
Okay, so we know what it is and where it lives. Let's get technical. Segment 4, the technical deep dive. For a lot of modern developers, COBOL looks alien. Let's break down its structure. How does it compare to, say, Java?
The absolute biggest difference you notice first is the syntax. COBOL is verbose. It uses English-like prose.
Like move X to Y.
Exactly. Or if account balance is less than minimum balance, then perform charge fee routine. The goal was self-documentation, readable by managers, not just coders.
Laudable goal, but I bet it makes for long programs.
Oh, incredibly verbose. There are over 300 reserved words. Critics call it flabby, clumsy. Compare that to Java or C# with their concise C-like syntax, curly braces, semicolons, operators.
COBOL uses periods for structure, mostly.
Yeah, the period is the main sentence terminator.
Yeah.
That plus the incredibly rigid column format.
Ah, the punch card legacy. Specific columns for specific things.
Column 7 for indicators, area A calls 811 for divisions, sections, paragraph names, area B calls 1272 for statements.
Yeah.
It makes the code visually very structured, but also very restrictive compared to modern free-form languages.
And that rigidity extends to the overall program structure, right? The 4 divisions.
Absolutely mandatory. Every single COBOL program has them in order. First, identification division. Just names the program, author, date, that kind of stuff.
Yeah.
Simple.
Okay.
Environment division. This is crucial for portability. It's where you define machine-specific things, the computer it's compiling or running on, file assignments, linking logical file names in the program to actual physical files, character sets.
So that isolates the hardware dependencies. Clever. Third,
The big one for business, data division. This is where all your variables, records, file structures, everything gets declared. And it's where COBOL really shines for business data.
because of the hierarchical structure, the level numbers.
Precisely. You use level numbers like 01 for a main record, like a customer record, then 05, 10, 15 for subordinate fields within that record, like name, address, account number. It maps directly to how businesses think about data hierarchies.
And the picture clause, or PIC. That's about defining the exact format.
Exactly. PIC is fundamental. It defines the data type, size, and memory layout explicitly. PIC 97 is a 7-digit integer. PIC X20 is a 20-character string. PIC S95 V92 is a signed number with 5 digits before an implicit decimal point V and 2 after.
That V for the implicit decimal forces you to think about precision up front. Crucial for money.
Absolutely crucial. Banks love it because there's no ambiguity about how financial data is stored and calculated. Modern languages often hide this, which can sometimes bite you with floating point weirdness.
And then there's the legendary level 88. What's that do?
Oh, level 88s. They're brilliant for business logic readability. They don't define data storage, they define a condition name. It's like a Boolean flag linked to a specific value in the parent data item.
Give me an example.
Okay, so you have a field customer status pick X1. You could define 88 active customer value A. Then in your code, instead of writing if customer status A, you can just write if active customer.
Much clearer to read, especially for a non-programmer understanding the business rule.
Exactly.
Yeah.
It makes the code read like business rules. Pure genius for its time.
Okay, on to the fourth division, procedure division. This is where the actual logic lives, and where the infamous spaghetti code reputation comes from.
Historically, yes. Early COBOL relied heavily on the GoTo statement, which could lead to unstructured messes. The perform verb was introduced to create loops and call subroutines, paragraphs or sections, which helped a lot with modularity.
But complexity could still creep in.
Oh, yeah. Things like perform THU let you execute a range of adjacent paragraphs, which could be confusing. And the big one. Traditional COBOL didn't really use a modern call stack. It used a continuation address.
Meaning it just knew where to jump back to, but didn't keep track of how it got there.
Pretty much. So trying to do complex nested calls, or especially recursion, which wasn't originally supported but people tried, could lead to unpredictable behavior, infinite loops, hence spaghetti code. The flow wasn't always clear.
And the absolute mind bender, self-modifying code, was that real?
Believe it or not, yes. Historically, COBOL had the alter X to proceed to Y statement.
Wait, it could change its own jump instructions while running?
Yep. It literally rewrote the target of a JogoTO statement somewhere else in the code, on the fly. It was an absolute nightmare for debugging and maintenance. You could never be sure where a JogoTO was actually going to go.
That sounds terrifying. Why would anyone even allow that?
Maybe for some obscure optimization back when memory and cycles were incredibly precious.
Yeah.
But it completely destroyed understandability. Programmers learned to fear the sight of a lone JogoTO because it might be altered from somewhere else entirely.
Thankfully, that got removed.
Oh yes. Mercifully deleted in the COBOL 2002 standard. Good riddance.
Okay, that technical context, especially the maintenance nightmares, it perfectly sets up segment 5, the human story, the COBOL talent crisis. And we have to start with Y2K.
Y2K, the Millennium Bug. It was fundamentally a COBOL crisis. Why? Because of that simple decision decades earlier to save precious memory space by storing years as 2 digits. YYMMDD.
And business applications are all about dates. Loans, insurance policies, expiration dates.
Exactly. So when YY rolled over from 99 to 0, billions of lines of COBOL code were potentially going to misinterpret 2000 as 1900, causing chaos. Calculations would be wrong, systems could crash.
And it wasn't like the original programmers were stupid. They just never thought the code would last 30, 40 years.
Precisely. Alan Greenspan, former Fed chair, actually admitted, "I am one of the culprits who created this problem." He said programmers back then never entered our minds that those programs would have lasted for more than a few years.
So fixing it,
Right.
How big was that effort?
Gigantic. Globally, fixing Y2K costs somewhere between $300 billion and $500 billion. Just think about that. A significant chunk, maybe up to 24%, was specifically COBOL remediation.
And the fix involved.
2 main strategies. Date expansion, actually changing the date fields to store 4-digit years. That was the best fix, but expensive and time-consuming.
And the quicker, dirtier fix.
Windowing. You leave the 2-digit year, but add logic that says, basically, if the year is less than, say, 25, assume it's 20 back X, otherwise assume it's 19 back S. Cheaper, faster, but a temporary patch, really.
But despite all the panic planes falling, infrastructure collapsing the world didn't end. The fix worked.
It was a massive success because the deadline was immovable, and governments and companies threw immense resources at it. We know critical systems like missile defense systems, nuclear plants, had issues in testing, but got fixed just in time. It held together.
Okay, but the Y2K effort highlighted the sheer amount of COBOL out there and the people needed to fix it, which leads us to the current crisis. The brain drain.
Yeah, this is the slow burn problem. The generation of programmers who built and deeply understand these decades-old COBOL systems, they're retiring fast.
And their knowledge isn't always written down.
Often it's not. It's locked away in institutional knowledge or operational know-how. Deep understanding of why the system works the way it does, the undocumented quirks, the business context, it walks out the door when they retire.
We saw this hit hard during the pandemic, right, with unemployment systems.
Absolutely.
Yeah.
Several U.S. states put out public pleas for COBOL programmers. Their old unemployment systems needed urgent updates to handle the massive surge in claims for new benefits programs. But they literally couldn't find enough people with the skills to go in and modify that critical legacy code quickly. It was a real crisis point.
So why is it so hard? If COBOL is English-like, why can't a smart Java or Python developer just pick up a manual and dive in?
Because the COBOL code itself is only part of the puzzle, often maybe the smaller part.
It's the ecosystem around it.
Exactly. Experts stress you don't just need a COBOL coder, you need an application expert, someone who understands the whole system. Why? Because crucial documentation, like detailed data dictionaries explaining what every field means, or system flowcharts, they often just don't exist.
No data dictionaries. How do you maintain anything?
Carefully. One veteran programmer reported working at 11 different companies over 36 years. None of them had proper, up-to-date data dictionaries for their core systems.
That's terrifying. So the knowledge is purely tribal.
A lot of it, yeah. And it's not just the COBOL. These legacy systems are complex ecosystems. You have the COBOL programs interacting with transaction monitors like CICS.
CICS handles the online screens and transactions.
Right, and specialized file systems like vSAM for high-speed data access, often mainframe databases like DB2. And critically, the whole world of batch processing orchestrated by JCL.
JCL, Job Control Language, the scripting that actually runs the COBOL programs overnight.
Yep, JCL tells the mainframe which COBOL programs to run, in what order, what data files to use as input and output, what to do if something fails. It defines the actual business workflow for batch jobs. Plus, you have complex job schedulers managing dependencies between hundreds or thousands of these JCL jobs.
So without understanding the JCL, the scheduler, the CICS transactions, the vSAM files, just reading the COBOL code gives you an incomplete picture.
Very incomplete. You don't understand the full business process or the data flow. That's why those retiring application experts who understand the whole interconnected system are irreplaceable. And that's the talent crisis.
Okay, that deep complexity makes the need for modernization clear, but also explains why it's so hard. Let's talk about that. Segment 6, modernization from COBOL to cloud. Why is change imperative despite the risks?
Because that stability often comes with rigidity. These old systems are usually monolithic, one giant code base. They have tight coupling between components, meaning a change in one place can break something unexpected elsewhere, and they run on outdated tech stacks.
Which hinders what? Agility, innovation.
All of the above. Businesses need to move faster, integrate with new services, use AI, leverage the cloud for scalability. Legacy systems often act like an anchor, slowing down that kind of innovation. So modernization isn't just technical, it's a strategic business move to unlock growth.
But it's not just flipping a switch. There are strategies, right? The 6 Rs.
Right. It's a spectrum of approaches, usually phased, balancing risk and reward. You start at the low-risk end.
Like rehosting. Just lifting the existing code and running it on a server in the cloud.
Exactly. Lift and shift. Minimal code changes. Or replatforming, where you make small tweaks so the COBOL can run on a different platform, maybe Linux instead of ZOS. These are faster, cheaper, but you still keep most of the legacy architecture.
Then you move up the ladder to more significant changes.
Yep. Refactoring is about improving the internal structure of the code, making it cleaner, more maintainable, without changing what it actually does externally.
Getting rid of some of that spaghetti code, maybe?
Hopefully. Then there's re-architecting. This is a major overhaul, breaking up the monolith, often into modern microservices, higher risk, higher reward.
And the final options are basically bitching it.
Pretty much. Replacing it entirely with a new system, maybe a commercial off-the-shelf package, or simply retiring the application if it's no longer needed. Re-architecting and replacing offer the most potential for agility, but they're also the riskiest and most expensive.
Now, if you're going to re-architect, you first need to figure out what the old system actually does. Extract those business rules, especially the undocumented ones. This is where domain-driven design comes in, DDD.
DDD is super valuable here. It's a methodology focused on understanding the business domain deeply. It forces collaboration between developers and business experts using what's called a ubiquitous language.
A shared vocabulary.
Exactly. A precise, agreed-upon language for talking about the business concepts. This clears up ambiguity. And critically for modernization, DDD uses bounded contexts.
Bounded contexts, like
Every-
drawing lines around different parts of the business.
Sort of. It's about defining clear boundaries for different domain models. This part handles customer management, that part handles order processing, this other part handles billing. Each has its own consistent model and language inside its boundary.
And how does that help get the rules out of the COBOL?
Because those bounded contexts naturally map to potential microservices or modern API boundaries. By modeling the business this way before you rewrite, DDD gives you a structured way to identify, understand, and preserve those vital, often hidden business rules that are embedded in the legacy code and its surrounding ecosystem.
Okay, so you use DDD to understand the what and why. Then you choose your target architecture, usually microservices these days.
Often, yeah. Small, independent services focused on specific business capabilities, and they need to talk to each other. Two main patterns for that.
API-driven architecture.
Right. That's mostly synchronous communication. One service calls another's API, maybe using REST, waits for a response. Good for requests that need an immediate answer, exposes business functions clearly.
And the other pattern, event-driven architecture, or ED.
ED. This is asynchronous. Services communicate by publishing domain events like order placed, payment processed, inventory updated to a message broker, something like Kafka. Other services subscribe to the events they care about and react accordingly.
That sounds almost like a modern version of batch processing in a way, things reacting to stuff happening.
It has that asynchronous feel, yeah. ED is great for decoupling services, improving resilience. If one service is down, events can queue up, and enabling real-time responsiveness across the system. It fits well with the kind of high-volume, transaction-based world COBOL lives in.
Okay, now, all this complexity, billions of lines, missing docs, tangled logic, it just screams AI. Can't we just point some fancy AI at the COBOL code and have it figure out the business rules?
That's the dream, and some startups are definitely pushing that, using AI, natural language processing, trying to parse the COBOL, visualize it as decision trees, and automatically extract the rules.
But the veterans are skeptical.
Deeply skeptical. You hear quotes like, what's AI going to do with that? Their point goes back to the ecosystem complexity.
The code isn't the whole story.
Right. They argue that true understanding requires context the AI can't get just from the COBOL source. It needs the data dictionaries, if they existed, the copybooks, reusable data structure definitions, the JCL that runs the jobs, the job scheduling information, all the operational stuff.
The why and how it actually runs, not just the what the code says.
Exactly. One expert put it perfectly. Programs are written to follow business rules set forth by the business. It's like analyzing the car to figure out where it came from. The code implements the rules, but the rules originate outside the code.
So the argument is AI alone is insufficient. You still need the human expert.
That's the strong consensus from experienced practitioners. AI might assist, but you absolutely need a human in the loop, those application experts, to interpret the code correctly within its full operational and business context. Full automation seems risky.
That distinction between code and context is crucial. Okay, let's look ahead. Segment 7, the future of legacy. What does it look like?
Well, it's probably not a sudden COBOL extinction event. It's more likely a long period of coexistence and careful integration.
Interoperability, making the old talk to the new.
Exactly. Modern COBOL compilers, like the ones from Micro Focus, actually provide features for this. You can have COBOL programs called Java methods and Java called COBOL programs. It allows bridging the gap.
But relying on those vendor tools could lead to lock-in, right?
It can, yeah. That's a trade-off. But the overall strategy often relies on that architectural pattern, the strangler fig pattern.
The strangler fig, explain that again.
Imagine a fig vine growing around an old tree. The pattern works the same way for software. You gradually build new functions or services around the old legacy system. You route requests to the new service where possible. Over time, the new system strangles the old one, function by function, until the old system can finally be switched off.
Minimizes risk by doing it piece by piece.
Precisely. It avoids the Big Bang replacement risk. But even with gradual approaches, the core argument against aggressive replacement remains.
The sheer reliability of the old system.
Yep, those mainframes are dead unreliable. And we've seen plenty of examples where large-scale COBOL replacement projects, especially in banking, have gone badly wrong. They become expensive and problematic, leading to major service outages, bad press, even regulatory fines.
So the known stability of COBOL is a powerful force for inertia, or at least extreme caution.
Absolutely. Why risk breaking something that, for all its flaws, actually works incredibly well at its core task?
Let's circle back to Y2K one last time. There was a lesson there, beyond just fixing the date bug.
Martin Thomas, who was involved in Y2K work, makes a really provocative point. He says, yes, the remediation was a huge success in averting disaster. It showed what focus and resources could do against a hard deadline. But the real lesson, he argues, the one about the need for fundamentally better software engineering practices, more modularity, better information hiding, building for robustness, that lesson wasn't really learned by the industry as a whole.
So because we didn't learn that deeper lesson,
We kept prioritizing, and still often prioritize, cost and speed to market over genuine robustness. He argues we're just building new kinds of single points of failure now. He points to things like the world's over-reliance on GPS signals for timing, or using encryption that might not stand up to quantum computing. We fixed the Y2K bug, but maybe missed the underlying disease.
that's a sobering thought. So this $300 billion dinosaur, COBOL, its stubborn persistence, what does it ultimately force us to confront?
I think it forces us to look beyond just the cost of rewriting code. It makes us confront the immense, often invisible business value that's embedded in that old, complex, but incredibly reliable legacy software. The stability, the correctness honed over decades. That's the really valuable thing. Understanding the existing system, not just replacing it, is the true challenge.
Wow, okay. So we've gone from COBOL's birth, driven by DoD efficiency needs, all the way to it's still underpinning 95% of our card transactions today.
It's an incredible journey, and the challenge now is twofold. Dealing with the sheer technical complexity of these massive aging code bases.
And the human complexity, that critical skills gap as the experts retire.
Modernization has to happen, eventually.
Yeah.
But it needs to be done with deep respect for the stability these systems provide. That embedded business knowledge is the hardest and most expensive thing to replicate or replace.
So we'll leave you, the listener, with this final thought to chew on. We know COBOL mainframes are incredibly reliable, handling global finance for over half a century. When we talk about modernization, is the biggest risk really the project cost? Or is it the potentially far greater risk of accidentally introducing instability, fragility, maybe even new vulnerabilities into core systems that right now essentially never go down?
That's the multi-trillion-dollar question, isn't it? What's the true cost of disrupting stability? A critical question about risk itself.
Indeed. That's it for this deep dive into the surprising resilience of COBOL. Thanks for joining us. We'll see you next time.